Hi class, in this video here we want to start talking about related rates. And what this is basically applications of the derivative in the chain rule. Okay, so what you'll see here is we'll work some like real world examples involving this concept of related rates. Okay, so in this section here's what we're going to do. The first thing we're going to do is we're going to talk about how you find a related rate. And then what we're going to do is we're going to use related rates to solve real world problems. And I have 3 or 4 examples picked out here that we'll work through. Okay, so for example, what is a related rate? What are we even talking about first? Okay, so you've seen how the chain rule can be used to find dy dx. All right. Another important use of this chain rule is to find the rates of change of 2 or more related variables that are changing with respect to time. Okay, so we have these 2 variables that are changing with respect to time. So this is going to be some variable t. All right, so for example, suppose you have water that's being drained out of this conical tank. So you have this tank here, has a little hole in it, and water's coming out of it. All right, the volume of the water. Okay, so just to note that the volume of the water. Okay, the radius of the water at the top here. Okay, and the height of the water as it's being drained are all functions of time, right? Like the volume is going to decrease over time, the radius is going to decrease over time, and the height is going to decrease over time, right? Because water's coming out. So these rates here, or excuse me, these variables change with respect to time. Okay, so we know that these variables are all related by this equation. Okay, so the volume of a conic here is V is equal to pi over 3 times the radius squared times height, okay? And the volume is going to change over time because the radius is changing with time and the height is changing with time. Okay, so you can differentiate implicitly with respect to t. Okay, watch what happens when I do this to find what we call a related rates equation. So I'm going to differentiate with respect to t, v. I'm going to differentiate with respect to one side, and I'm going to have to differentiate with respect to t the other side. Well, this right here, this is just dv dt, okay? The rate of change of the volume with respect to time. Now, r and h are each functions that are of the time variable t. So you're going to need to use the product rule here. So pi over 3 is a constant. So the derivative of r squared with respect to t becomes 2r, and then because of the chain rule here, you're going to need dr dt, and then don't forget you have h times h, you still have this h, plus pi over 3 times r squared, and now the derivative of h is just dh dt. So I'm just going to rearrange this so it looks a little bit nicer. Okay. So this is 2 pi over 3 r times h times dr dt plus pi over 3 times r squared dh dt. So look, this is what it's saying. The rate of change of the volume, okay, dv dt, depends on both the rate of change of the radius and the rate of change of the height. All right, and then what we're going to do here, what you're going to see is I'm going to give you some of these values, and then we're going to be able to solve for these rates of change. All right, so before we get into a real world example of this, let's just work a very, very simple equation so you can kind of see what's going on here. All right, so I have the variables x and y. Okay, so and they're related by this equation down here. Okay, y is equal to x squared minus x plus 1. Excuse me. And both x and y are differentiable functions of t. Okay. So what I want to find is I want to find dy dt when x is equal to 1. Okay. Given that dx dt is equal to 3 when x is equal to 1. All right, so here's what I'm going to do. I want to find dy dt. So I'm going to differentiate both sides with respect to t. All right, so the derivative of y with respect to t is just dy dt is equal to. Now I'm differentiating x squared with respect to t. Okay, so this becomes 2x times dx dt minus the derivative of x with respect to t is just dx dt. And a derivative of a constant here, it doesn't matter that it's with respect to t here. That's just still 0. So now look, I want to find dy dt when x, which is our variable here, is equal to 1. And look, dx dt, which is given right here, is equal to 3. So dy dt is equal to 2 times 1, because that's what I'm saying what x is, and dx dt is 3 minus 3. Okay. So this is equal to 2 times 3 is 6, 6 minus 3. This is equal to 3. Just so happened that it ended up being the same thing, but that's not necessarily how it will always work out here. Okay, so you're seeing the process. You need to use the chain rule. You need to remember the chain rule. Okay, so I'm going to highlight that. All right, so if I have the derivative with respect to t of any variable, okay, like x cubed, all right, or, r or v or h, whatever, as long as the variables are different, the variables do not agree. So with respect to t, but x cubed here, this becomes 3x squared, and then you have dx dt. Or, for example, if you have the derivative with respect to time of like radius squared, like I did in the previous example. This is 2r, and then you need dr dt by the chain rule. Okay? All right, so now let's talk about how you solve related rates problems, okay? And we're going to do a number of problems. All right, and we'll start with easy ones and work our way up. Okay, so the first thing you're going to do is you're going to identify all given quantities and quantities to be determined, and if needed, also sketch the problem. So there'll be one problem where I'll do a sketch. Then you're going to write an equation involving the variables whose rates of change either are given or to be determined. You're going to use that chain rule, implicitly differentiate both sides of the equation with respect to time, t, okay? And then just like I did on the previous slide, you're going to substitute in the resulting equation, all known values for the variables and their rates of change, and then you're going to solve for the required rates of change. So these problems, okay, they do seem a little weird at first and difficult at first, but after you watch me go through my examples here, so I'm going to do, looks like I've got 1, 2, 3, I've got 4 examples here, okay? And after, what you're going to see is there's going to be a pattern that develops, and it will click. I promise you, it will click. Okay, so here's the first problem. So a pebble is dropped into a calm pond. Okay, so you're just taking a pebble, right, and you're just dropping it right into the water. And when you do that, right, ripples start forming out of the water. Okay, so ripples causing ripples in the form of concentric circles. So as you see here, are shown in the figure below right here. The radius r of the outer ripple is increasing. So look what you're given. You're given something about the radius r, all right, is increasing at a constant rate of 2 feet per second. So right here, you're given a rate of change of some type. When the radius is 5 feet, so you're given something else, at what rate is the total area of the disturbed water changing? So they're asking you to find the rate of change of the area. Okay. Identify all quantities, all given quantities and quantities to be determined. Okay, so right off the bat, the radius r of the outer ripple is increasing at a rate of change of 2 feet per second. So what you're given there, you're given the rate of change of radius. Okay, you're given dr dt. Okay, that's the derivative, right? Rate of change. So this is 2 feet per second. So then you're asked now to find, okay, all right, at what rate is the area of the total area changing? So you're asked to find rate of change of the area which is dA dt, when the radius is 5 feet. Okay, so what you need here, okay? You need, next it says, write an equation involving the variables whose rate of change either are given or are to be determined. So look, you need a formula that relates area to the radius of a circle here, okay? So to do that, you're just going to use the equation for the area of a circle. Okay, so what is that? You know, area of a circle is equal to pi r squared, right? Now look, the variable a and the variable r, you know, you have them related to each other in equation. Perfect, perfect. Use the chain rule, implicitly differentiate both sides of the equation with respect to time. So you're going to take the derivative with respect to time of a and the derivative with respect to time of pi r squared. Okay. This right here becomes dA dt, which is what you're trying to find, is equal to. All right. Now differentiate this. The 2 comes down, so this is 2 pi r and then dr dt. Well, now let's see what happens. Substitute in the resulting equation all known values for the variables and the rates of change. Well, look. R, we know R is 5 feet. Oh my gosh, and look at this. We know dr dt is 2 feet per second. So this is 2 pi, R becomes 5 feet. Dr dt is 2 feet per second. So what is the rate of change of the area here? All right, well, 2 times 5 is 10 times 2. This gets me 20, and then don't forget you have the pi. And then you need to make sure you have the units right. So feet times feet get me feet squared per second. And that's it. So you know, what is the rate of change of this, the area of this outer circle? Well, when the radius is 5, okay, the area is changing, excuse me, at 20 pi feet squared per second. So again, it really was just figuring out what's given, what you're being asked to solve for, and then an equation here that will help you. All right, let's try another one here. So air is being pumped into a spherical balloon at a rate of 3 cubic feet per minute. Okay, so you're given a sphere, and they're telling you air is being pumped into it, and they're telling you the rate of change is 3 cubic feet per minute. So the cube there of the cubic feet tells me it's going to be volume. So it says find the rate of change of the radius when the radius of this balloon is 1 foot. Okay, so first off, what are you given? You're given the rate of change of the volume, okay? So you're given dV dt, the rate of change of the volume. And this is 3 feet per minute, or 3 cubic feet, excuse me, per minute. And they want you to find the rate of change of the radius. They want you to find dr dt, the rate of change of the radius, when the radius is equal to 1 foot. All right, so what you're going to have to do is you're going to have to go, you know, if you don't know off the top of your head, you can go look for the volume of a sphere. Volume of a sphere here is equal to, or its volume is equal to 4/3 pi times the radius cubed. Okay, so now you can see the pattern. Well, look, I'm asked to find dV dt. I've got the variable v here. And I'm given, or excuse me, I'm given dV dt, and I have the variable here. Sorry about that misspeak there. And I'm trying to find dr dt. Well, I have the variable here when r is equal to 1. So this equation figures it out for us. So you're going to differentiate both sides with respect to t. So this here becomes dV dt is equal to, all right, you bring the 3 down, right? So the 3 and the 3 here in the denominator will cancel. So you're just left with 4 pi r squared and then dr dt. All right, so plug in what you know. So dV dt here is 3 feet cubed per minute is equal to 4 pi, And then my radius is 1 foot squared. All right, dr dt. So what are you going to do? You're just going to divide all of this over, and you get, I'm just going to move the dr dt over. Dr dt is equal to 3 cubic feet per minute divided by 4 pi, you know, the 1 squared is 1, feet squared. So what's going to cancel here? Feet cubed, feet squared. You're just left with 3 over 4 pi feet per minute is what the radius is changing at there. So again, it's just about, you know, looking through the problem, figuring out what you're given, and you know, and then realizing what equation you're going to need to that relates to the variables, and then you're going to just have to differentiate with respect to time. All right, let's do I don't know, let's do one that's a little bit harder, okay? And here's the problem. At a sand and gravel plant, okay, sand is falling off a conveyor and onto a conical pile, all right, at a rate of 10 cubic feet per minute, okay? The diameter of the base of the cone is approximately 3 times the altitude, and that's the height, okay? So altitude is the same thing as height. At what rate is the height of the pile changing when the pile is 15 feet high? Okay, so a lot is going on here, all right? So for this problem here, I'm going to actually draw a picture so you can see what's going on. Okay, so you have this conveyor, and what's falling off the conveyor is sand. So here's the conveyor, let's just say. All right, so this is the conveyor. And sand is falling off of it. And what it's doing when it falls off to it is it forms a conical pile, so like a cone, okay? So here's the cone that's being formed on the ground here. All right. Okay, so let's see what we're given, okay? So first off, what are you given? You're given, okay, the sand is falling off onto the pile at a rate of 10 cubic feet per minute. So again, what you're given is you're given the cubic feet tells me the volume is changing. So dV dt is equal to 10 cubic feet per minute. And then this is the next piece we're going to have to figure out here. The diameter of the base of the cone is approximately 3 times the altitude, so the height. So here's the height. All right, and that means the diameter here, okay, this diameter is equal to 3 times the height. But if you're thinking back, you know, usually, always, these volume formulas are in terms of radius. So, you know, the radius is half the diameter, so the radius is 3/2 the height. At what rate is the height of the pile changing? So they want you to find dH dt. Okay, find dH dt, all right, when the pile is 15 feet high. All right, so again, you're going to use the volume equation here. So you're going to use volume, which is equal to 1/3 pi r squared h. Well, look, do you notice anywhere in here you have V and H. V and H are up here, but there's no R here, okay? So what's going to happen here? Well, you're going to have to get rid of the R variable by plugging in 3/2 H for it here. So you're going to have to plug in 3/2 of H is equal to R, because otherwise there's just too many variables for this. You don't know what the radius is changing. So volume is equal to 1/3 pi. Now my R is 3/2 squared times H. Well, 3/2 H, sorry. So volume is equal to 1/3 pi. When I square this becomes 9/4 H squared. And then don't forget you have this H. So the 3 will cancel with this 9 to make a 3. So my resulting equation I'm going to use here, okay? And this is because the diameter is 3 times the height, okay? It's going to end up being, the 3 is going to cancel with this 9. It's going to end up being 3/4 pi. And then look, h squared h gets me h cubed. Okay, so I'm going to use this equation now, all right? So I'm going to go to the next slide here, okay, so that you can actually see the work. So you know what? I boiled it down to a single equation, right, that relates the variables, okay? So now I'm just going to follow the rules. Differentiate both sides with respect to t. All right, and remember these, okay? dv dt is 10 cubic feet per minute, and we want to find dh dt when the height is 15 feet. All right, so I'm going to differentiate both sides with respect to time. All right, this equation right here, volume, is equal to differentiate with respect to time, 3/4 pi r cubed. Okay, dv, this is dv dt, is equal to, okay, 3/4 pi. Now, remember, when you bring, you're going to have to differentiate r cubed. So you're going to bring the 3 down. 3 times 3 gets me 9/4 pi r squared, or excuse me, I made a little mistake there. Sorry, I wrote the r, h squared. H, and then dh dt. Sorry for that little typo there. Okay, so now let's see what we're given here, okay? dv dt is 10. I'm going to leave the units off for the end here, okay? Because the height is only going to be in feet per minute, okay? Because it's just the height here. So we'll tack those units on at the end. So volume is changing, 10 cubic feet per minute is equal to 9/4 pi. And then we wanted the height. The height was going to be 15 feet. So this is 15 squared. And then dh dt, all right, that's what we're looking to find. So look, now I just got to solve for dh dt. It's very simple. 10 is equal to 9/4 pi. 15 squared, I believe, gets you 225. And then you have this dh dt. 9 times 225, so you get, that ends up being 2025 pi over 4 dh dt. And then look, you're just going to multiply both sides by 4 divided by 2025 pi. All right, so you get basically, if you want to think about it, as you're cross multiplying too. So you get 4 times 10 gets me 40 divided by 2025 pi. And look, 5 will go into both of those things. So when you simplify, you're left with 8 divided by 405 pi. Okay, and then you got to remember this is feet per minute, and that's what your height is changing, the rate of change of your height in that case, dh dt. All right, so again, so for this one here, maybe it helped to see the drawing and then figure it out. I got diameter here, but I remember diameter, radius is half of the diameter, so then I can get it all in terms of a single variable on the right hand side of h. All right, let's end on this one was a little bit harder, but let's end on an easier one then, just so you can see. All right, so the problem goes like this: all edges of a cube. So we have this cube. All right, so I'm going to do a drawing here. So I have this cube. And they're all expanding, okay, at a rate of 6 centimeters per second. So we know a cube, all the sides are the same. Okay, so you're given what the rate of change of the sides. So I'll even write that in here. You're given ds dt is equal to 6 centimeters per second. So it's how fast is the volume changing? Okay, so it's asking you to find dv dt when each edge, and then it has two parts. When A, S is equal to 2 centimeters, and B, S is equal to 10 centimeters. All right, this is a piece of cake. So you need an equation that relates the sides to the volume. Well, you know, a volume of a cube is given by, you know, volume is just equal to side cubed, right? So differentiate both sides, right? So you get derivative with respect to t of v is equal to the derivative with respect to t of s cubed. So you get dv dt is equal to 3s squared ds dt. So look, I'm asking you to figure out how fast the volume is changing. So when I give you, look, I'm giving you s, and there's a constant rate of change here of 6 centimeters. So the first part, A, dv dt is equal to 3 times 2 centimeters squared, and then ds dt is 6 centimeters per second. Well, 2 squared is 4. 4 times 3 is 12 times 6. This is going to end up getting me 72 centimeters squared times centimeters cubed per second. In B here, dv dt is equal to 3. And now I'm saying, well, what happens when it's at 10 centimeters? So 10 centimeters squared. And then ds dt is still 6 centimeters per second. So 10 squared is 100. 100 times 3 is 300 times 6. This is 1800 centimeters cubed per second. All right, which is what we think, right? You know, larger volume, the volume would be changing quicker there. All right, class, those were 4 quick examples. And again, you know, the key, you know, word problems are always tough. So you have to write down what you're given, what you're asked to find, and then an equation that relates it all to, you know, but, and it's okay if you don't remember, you know, what the volume of a cube is or volume of a sphere, you can very quickly look that up. And as always, I'm here for help.